Right, this lesson is about nanoscience. We'll take a look at nanoparticles and we'll take a look at fullerenes. But before we do that, here's a quick retrieval. So pause the video here and have a go at these 5 questions, please. Okay, let's have a look. So question 1, what are the 3 subatomic particles? Well, you should have said protons, neutrons and electrons. Protons and neutrons are found inside the nucleus. Electrons orbit the nucleus in shells. Number 2, which is the lightest subatomic particle? Is the electron. In fact, its mass is negligible when it comes to the mass of the atom. Number 3, which subatomic particle has a positive charge? It's a proton. P for proton, P for positive. Which subatomic particle is able to carry a charge through a material? Is the electron. And name 2 models of the atom. Well, J.J. Thomson put forward the plum pudding model, and then that was replaced by the work done by Rutherford by the nuclear model of an atom. So that's the objective, and we're going to take a look at advantages and disadvantages of nanoscience, and we're going to take a look at how describing the structure of nanotubes and fullerenes. If you look at this, you've got 2 pictures here, both showing cubes. However, one cube has been chopped up into smaller little cubes. So what you do is, if you calculate the surface area, the cube on your left-hand side has a surface area of 96 centimeters squared. So what's the advantage of chopping up this cube into smaller cubes? Well, let's have a look. That's the advantage. Look what's happened to the surface area. So by crushing something from a large piece into small powder form, you increase the surface area. And if you increase the surface area, it increases the rate of a reaction. Things can happen a lot faster. In a reaction, nanoparticles are able to react more quickly because more atoms are in contact with a reactant compared to a larger particle. It's to do with nanoparticles being so small, they have a large surface area. If you look at these 2 pictures there, this one here has a low surface area to volume ratio, whereas you chop it up, you end up with a high surface area to volume ratio. Nanoparticles have a much bigger surface area to volume ratio than particles size, so they react very fast. And as the size of a cube decreases by a factor of 10, the surface area to volume ratio will increase by a factor of 10. Moving on. And there you go. Nano means dwarf in Greek. Nanoparticles may have properties different from those for the same materials in bulk. Make a note of that. And that's because of their high surface area to volume ratio. It may also mean that the smaller quantities are needed, okay, to be effective than for the particle with normal particle size. Here's some facts for you. Here's something that you may want to pause the video and read yourself. Okay, moving on then. Put the following in order, starting with the smallest. Fine particle, there's the size. Nanoparticle, atom, subatomic particle, and a coarse material. So pause the video here and put them in order. Put them in the following order, starting with the smallest. So what you should find, the smallest is your subatomic particles, your protons, your neutrons, and the electron, followed by the atom, and then it's a nanoparticle, and then it's a fine particle, and then you've got the coarse particle. Moving on. Nanoparticles. Nanoscience may lead to the development of... So nanoparticles, or the whole field of nanoparticles, which is nanoscience, has led to development of new catalysts, new coatings on materials, new computers, stronger and lighter building materials, and sensors that detect individual substances in tiny amounts. So you can see the importance of nanoscience. Some uses, actual uses. Nanoparticles are used as catalysts, okay, to speed up the reaction, and can be used in self-cleaning ovens and windows. And these are typical questions they will ask you for the uses of nanoparticles. Regular size titanium dioxide is used in house paint and certain sweet-coated chocolates. Titanium dioxide nanoparticles are used in sun creams to block harmful UV without appearing white on the skin. So that's another use. We're now going to take a look at fullerenes. Carbon can form fullerenes. Fullerenes is an allotrope of carbon. Fullerenes are molecules of carbon atoms with hollow shape. The structure of fullerenes is based on a hexagonal ring of carbon atoms. And you can see that from here. Hexagonal ring of carbon atoms. But they may also contain rings with 5 or 7 carbon atoms. And the first one ever that was found to be discovered was the Buckminster fullerene, and it's made up of 60 carbon atoms. It is spherical and contains about 60 carbon atoms. Buckminster fullerene. Fullerenes may be used for drug delivery systems, lubricants, and catalysts. The tube fullerenes are called nanotubes. These are very strong and are useful in reinforcing structures where lightness and strength are needed, e.g. in tennis racket frames. Carbon nanotubes are cylindrical fullerenes with very high length to diameter ratios, and their properties make them useful for nanotechnology, electronics, and materials. Graphene is another allotrope of carbon. It's a single layer of graphite and has properties to make it useful in electronics and composites. And one thing you'll find here, if we look at this carbon atom is bonded 1, 2, 3. Is bonded to 3 of the carbon atoms, which means carbon, which has an atomic mass of 12, atomic number 6, it's got 6 electrons, which means it'll have 2 electrons in the outer shell, 2 in the first shell, 4 in the outer shell. Because this carbon is using 1 electron there, 1 electron there, and 1 electron there, it's using 3 electrons, but it has 4 in the outer shell, which means 1 electron is able to move, delocalized electron, which means graphene, because it has a delocalized electron, is able to conduct electricity. Same as graphite. Graphite also has 1 delocalized electron. Moving on. Here's an exam question. You can pause the video. Okay, let's look at the question then. Tick the best description of a nano-sized layer. 1 mark. A layer 1 atom thick, a layer a few hundred atoms thick, and a layer millions of atoms thick. Well, the answer is, it's only a few hundred atoms thick. Suggest 2 ways in which using nano-coated tennis balls would be good for the environment. So let's have a look. Less material, save resources, less energy, less fuel, less pollution, less greenhouse effect, less global warming, less waste. Question 2. The picture shows a copper kettle being heated on a camping stove. Copper is a good material for making a kettle because it has a high melting point and it is a very good conductor of heat. Explain why copper, like many other materials, has a high melting point, and your answer should describe the structure and bonding of a metal, worth 4 marks. So pause the video here. Okay, let's have a look. Worth 4 marks. So it's a giant structure. It's made up of 3 electrons, delocalized electrons. Number 3, with strong bonds, strong attraction. Number 4, so a lot of energy is needed to break these bonds, strong force of attraction. Aeroplanes contain many miles of electrical wiring made from copper. This adds to the mass of the aeroplane. It has been suggested that the electrical wiring made from copper could be replaced by carbon nanotubes, which are less dense than copper. The diagram shows the structure of carbon nanotubes. There you can clearly see that's a carbon atom, and it's bonded to 1, 2, 3 other carbon atoms, using up 3 electrons, leaving 1 electron free, which we call delocalized. What does the term nano tell you about carbon nanotubes? It's only worth 1 mark. And nano simply means they're very small. Like graphite, each carbon atom in the carbon nanotube is joined to 3 other carbon atoms. Explain why the carbon nanotube can conduct electricity. We've already touched on this, so pause the video and see if you can answer this. Okay, moving on. So, it can conduct electricity because it only uses 3 electrons to bond with 3 other carbon atoms, so it has 1 free delocalized electron, and that electron is able to move. And that's the end of the lesson on nanoscience.